So our next distinguished speaker is a colleague and a friend, is James Kuffner. He's from Toyota Research Institute. He's been 6 years in Japan. Now he's back to the Bay Area. James, floor's yours.
Well, thank you very much. It's my great pleasure and honor to be participating, and thank you to the organizers for inviting me. I think all of us share a love of computers, and for me, I got started in robotics when I had a fascination with computers. And Tamim had asked me to reflect on 30 years of working on robots, but also maybe hopefully share some things that I may have learned on the way to help maybe some of the many young people who I'm very excited to see in the audience. And the computer as the most complex machine that humans have designed. In fact, it's so complex now that we need a computer to design the next generation. But something magical happens when you embed that computer into a physical system that can actually impact the world and change the world. And for me, when computers became so powerful that we aggregated their power and we networked them so that now we have this data center, many new things were possible. And that happened halfway through my career in robotics. And so I got very, very interested in how we can leverage the power of a modern data center in cloud computing to make cloud-connected vehicles and also robots intelligent. So for me, one of the things that I learned early when I was studying robots was that all the robots that were working in factories, like this Toyota factory, have structured environments. But if you try to transition from structured environments to unstructured environments, it leads to this research snowball, which is now I've got unknown objects and unknown obstacles, which means I have to do online perception, and I have to model. But that means I can't cheat with a priori models like I could in a structured environment. I also need to do online computation of motion, so I can't use predefined trajectories because the environment is unknown. And that means also I may potentially need to do dynamic tasking, because I can't rely on predefined sequences of motions. And so this has been my fascination, is try to find a way to create and embed this kind of reasoning so that robots can move out of factories. And I am particularly fascinated with search-based artificial intelligence. And of course, when I was a grad student, Garry Kasparov was defeated by IBM's Deep Blue in chess. And many people said, well, it'll take another 50 years before human player in Go is defeated by a computer. Of course, we all know that happened in 2016 with AlphaGo, much earlier than many people had suspected. But search-based artificial intelligence is benefiting from Moore's Law tremendously, and I consider planning and learning both search-based AI, because optimization that's happening, whether you're tuning the parameters of a neural network, it's essentially doing function approximation across many, many different large data sets, is able to leverage the power of computers to search and process many, many amounts of data. So I got interested particularly in humanoid robot motion planning through different collaborations and when I was teaching at Carnegie Mellon. And this is a hard problem because now you've got many degrees of freedom, you have real-time constraints, you've got balance. And so it was a really interesting challenge to try to tackle. And of course, the configuration space is large, and that means that many of the classical search-based planning approaches didn't scale. So this is right at the time when sampling-based planning was starting to emerge, and I had the great fortune as a grad student to collaborate with a postdoc in the lab, Steve Laval, who taught me a lot about planning and sampling, and we developed this algorithm, RT Connect, which does bidirectional tree-based search for single query planning, and we were able to embed this algorithm in many, many different robots. So over the next several years, I used this robot algorithm to motion plan real-time trajectories for arms so that I could grab things. And then after it grabbed it, it would then plan a new motion using RT Connect to then pick up the bottle and then deliver it. And of course, I had many collaborations with some of the people in the room, also extending the algorithms and trying to utilize this technique to scale. And one of the things I learned was this algorithm is nice because if I have a million-dimensional problem with no obstacles, it just goes right to the goal, like gradient descent. And that is a beautiful fact of this type of search technique, which is trying to focus the computation and scale with problem difficulty. The other thing, what was really important is if you want to manipulate something, you really have to actually make contact. Even though most of motion planning is avoiding obstacles, suddenly, if you want to manipulate something, you have to make contact. And we worked a lot on trying to figure out how to automatically decide the best way to grasp something. And of course, we use lots of physics-based simulations, but one of the successful collaborations I had with Ken Goldberg's group was really trying to leverage the cloud so that we could actually run a big job overnight and measure with perturbations and noise injection what are the stable grasps for this type of object, and then index those and then template match them. So some people talked about robot dreaming, but I always thought that what we really should be doing is robot meditation. I want the robot to go to sleep, use the cloud, dream about all the best ways to pick things up, and then wake up enlightened. The other thing I looked at was navigation. So here's another planning problem where you have unstructured environments. You might have objects on the floor. You might have objects that you may need to use dynamic motions to get across. And so we were looking at how we could scale some of these dynamic tasks to robots with different dynamics and capabilities. And I want to pay tribute to two of my colleagues who unfortunately passed away far too early. My student, Mike Stillman, who was a professor at Georgia Tech, and also my colleague, Satoshi Kagami, who I worked with for 20 years. They helped collaborate on something which I thought was quite unique, which is combining planning about manipulation with planning about navigation. And what was nice is that you could then combine sort of reasoning about creating free space as part of a sequence of operations as a behavior at the higher level, and then plan automatically manipulation tasks to move obstacles out of the way to create free space for navigation, which was a capability that these robots have. Finally, it became clear that it was going to be a while before we're going to have these humanoid robots in the home, but automated driving was really advancing with the urban challenge teams, and I got really excited to join this project at Google. So I was one of the first 12 members of the Google project, and later Vincent is going to tell you a lot more about Waymo and what they're doing now. But when I was part of that team, one of the things that we really realized was that I thought at first that we were going to make the safest car, so that all we had to do was look at the California DMV rulebook and make it follow the rules perfectly. And then it would be the best driver. It turns out if you do that, you can never get something working because the rule book will say you have to have 12 car lengths between cars before you merge on a freeway, and that just never happens. So one of the early accomplishments that we had was what we called the Larry 1K. We completed 1,000 miles of high complex routes of 100 miles each without human intervention, and I was the safety driver on 3 of those routes. And it was very, very convincing to me that we had to focus on safety and quality and test the code well, because the rule was I had to be the safety driver for my own code changes. So it very was motivated you to do well. And in order to productionize a lot of this technology, what I realized was that you could create a lot of the perception components, the planning components, and you could actually deploy them into production now by partnering with a car maker. And so I joined Toyota to really invest in their mobility technology and establish the Toyota Research Institute with Dr. Gil Pratt. And one of the things that we looked at was we were benefiting from the incredible advances in perception and deep learning to do image recognition and fusion. But one of the things that I learned was that in order to create the onboard software for automated driving, that was actually a small amount of code compared to what else you needed. You needed machine learning tools for labeling and training. You needed developer tools for doing code reviews and CIT. You had simulation tools and deployment tools, and also managing all the data so that you could then retrain your systems, and then, of course, deal with maps. And so in total, about 90% of the software you need is off-board. But you need that off-board software in order to create high-quality and safe onboard software. And of course, one of the great things is, in the spirit of cloud robotics, we can fully leverage cloud-based testing and simulation. And I think this is actually something really exciting that many people are embracing now, is how can we accelerate the occurrence of edge cases that otherwise might take years to naturally observe in the world. We can actually artificially increase the probability of those edge case situations and test them virtually and make sure that we have no software bugs and that the system responds. Now, of course, eventually we have to integrate and we have to test everything on the hardware, but I think simulation and accelerated testing and validation with simulation is actually going to be key for the future of many intelligent systems and robots. And it's not just the simulation of analytical models. I believe machine learning can fill in the gaps of our analytical models. So you have an analytical model, mathematical equations describing the physics and kinematics in motion, but you also have statistical models, things that you get with data that you couldn't model with equations. And I think this is going to be really, really exciting. Here's an arm farm that Toyota Research Institute did that virtually picks up many, many objects. This is part of the robot meditation, learning. And so finally, my dream came. I was able to work with many talented people in Japan to launch automated driving. It's a hands-off level 2 system that's in production now on the Lexus and the Toyota Mirai. And just some personal observations about all that work on autonomous driving. Traffic is actually a social behavior. You have to communicate with other drivers. And the other thing is, the safest autonomous vehicle is not one that follows perfectly the rule books. It's actually the car that drives like the median driver. If you're on either end of the spectrum, you're actually unsafe. And the reason is, human drivers can better predict the behavior of an autonomous car that drives like the median driver. So finally, I'll just share you some things that I learned about model-based design. I believe these complement each other, and that, as I mentioned, we can fill the gaps of analytical models. And an example would be machine learning that optimizes the parameters to compute candidate trajectories for driving, but then uses an actual control model that's designed with safety envelopes to be safe. And finally, I think if you ask artificial intelligence, that term, if I was to say I've got someone who's a chess prodigy, very, very intelligent, high IQ, to drive you, or a New York City cab driver who didn't graduate high school but has never had an accident in 50 years. So there's something that's different that it's measuring there in the skill. And I think, to me, planning, logic, and reasoning provide a machine with intelligence, but actually machine learning and data-driven techniques are actually providing experience. So for me, when I think about machine learning, I say, this is not AI, it's AE. It's artificial experience, or another word might be artificial wisdom. Because somebody who has long life experience, we say, has wisdom. And that's kind of what we're providing these machines. So to conclude, I think building safe, intelligent robots is really hard. But let us persevere with humility. And safety and reliability go hand in hand. So if you want safe systems, you have to make them reliable. And that means you need both robust hardware and robust software. If either one of those is weak, you have a weak robot that is not safe. We have to utilize our best-in-class tools for CI/CD, deployment, and testing. And we should leverage what computers are good at. Billions of calculations per second, processing big data, simulation, emulation, unified planning and learning, and I believe that this fleet intelligence and cloud robotics is a way that we can accelerate progress. And a best practice for safe intelligent systems is, I believe that the highest level of logic for a robot should be designed and validated by a human. Thank you very much.
Thank you, James. While the next speaker set up very, very brief question, if any, because we're running out of time. So,
I have a short question.
yes.
I think you mentioned it already a little bit. What's still missing in the autonomous driving is, I think, a system which knows how far it can bend the rules to still be accepted by the other drivers. Or is it? I think it's the most important thing to solve. What's your opinion on it?
Yeah, I mean, as I mentioned, if we can somehow collect enough data to estimate the median, then that is the behavior that I would recommend, because it's the one that's most predictable by other human drivers. And the interesting part about it is that it is local. People drive differently in Tokyo or Mumbai or New York or London. So we need to leverage the median in a sense of a real local and regional behavior. But the good news is that the data-driven algorithms can actually scale well. We can code it once, collect data, processes, and then bias those behaviors depending on the geolocation. I hope that answers your question.
Thank you very much again, James.
Thank you.